everyone. Today we're starting Module 6, which is all about solutions. And we've talked about solutions a little bit before, but we're just going to dive a little bit deeper into the concept. So in this module, we're covering 5 sections in your textbook, sections 9.1, 9.2, 9.4, and 9.5. And then we're also covering 11.6. All right, so let's start with Chapter 9. So previously we have talked about solutions and how they are homogeneous mixtures of 2 or more substances. And solutions form when there is sufficient attraction between the solute and solvent molecules. So remember, a solute is the substance that's present in the lesser amount in a solution, and the solvent is the substance present in a greater amount. So in the example shown in the figure on the right, we have salt added to water, and salt is present in a smaller amount, so it's the solute, and water is present in a larger amount, so it's the solvent. And water is typically our solvent, although you can have different solvents. So you need sufficient attraction between the solute and the solvent. All right. So solutes, again, those are present in a smaller amount. That can be a liquid, a gas, or a solid. So remember, previously we talked about something called solubility. And we said that something like a solid or a liquid can be soluble at higher temperatures versus gases, which are more soluble at lower temperatures. So just something to remember. Now, solutes are spread evenly throughout a solution. So they're spread evenly. Solutes also mix with solvents so that the solute and solvent have the same physical state. So for instance, when we add salt to water, everything mixes so that we have an aqueous solution. Now, solutes cannot be separated by filtration because they're evenly distributed throughout the solution and they're dissolved, but they can be separated by evaporation. So for instance, with our example of salt and water, if we let that beaker sit out in the sun, the water will eventually evaporate and we'll just be left with the salt molecules. Now, solutes are also not visible, but they can give a color to the solution. So one example is copper sulfate, or copper 2 sulfate, I should say. And if we initially add copper 2 sulfate to water, let's say initially it's not really spread out, but if we mix everything, and as copper 2 sulfate dissolves, eventually the particles are going to spread out in the water. And copper 2 sulfate also gives a solution a bluish color. So the solid is blue, and if we add it to water, eventually the water will turn blue as well because it's mixed with copper 2 sulfate. Okay. Now again, remember that you can mix different types of solutes and different types of solvents. So for instance, you could mix 2 gases together, and one good example is air. Air is made up of multiple gases. So nitrogen is the gas that's present in the largest amount. So air is usually composed of 78% nitrogen and about 21% oxygen. And then the rest is made up of things like CO2 or argon, etc. Now, you could also mix a gas with a liquid. And one good example is soda water. So Carbon dioxide is the gas that's mixed in with your solvent, and that is water. You could also mix a liquid with a liquid. So vinegar, for instance, is usually a dilute solution of acetic acid, shown here. So in that case, acetic acid is the solute because it's present in a smaller amount, and then water is our solvent. And then, of course, you can also mix a solid in a liquid, which we've seen multiple times. So one really good example is sodium chloride or table salt mixed with water. Now, there are some cases where you can mix a solid with a solid. And one example that we have seen previously is brass. So brass is actually a mixture of zinc and copper, although copper is usually present in a larger amount. So that would be our solvent, quote unquote. And then steel is another example of a mixture of a solid with a solid. So steel is made up of carbon and iron, and iron is usually present in a larger amount. So you can have all sorts of different solutions. It's not just liquids mixed with liquids or solids mixed with liquids. You can also have gases mixed with gases, or gases mixed with a liquid, or you can have a solid mixed with a solvent, or a solid. Too many S words. So there's all sorts of different examples of solutions. Now, previously we have talked about water as our solvent, and we discussed how water has partial charges, which is what makes it a really great solvent. So because water has a partial negative charge on the oxygen and partial positive charges on the hydrogens, that means we have polar bonds within the molecule. So if we redraw our molecule there, in water, hydrogens are not directly opposite from each other. They're actually both on the same side of the molecule. Later on in general chemistry, you'll learn more about molecule shapes, but we just don't cover it in this course. So even though you could draw the Lewis structure of water like this, where the hydrogens are directly opposite, that's actually not how the structure of water looks. The hydrogens are actually at an angle. Now, that means that we have electrons kind of going up towards oxygen. And so oxygen gets that partial negative charge, and the hydrogens have partial positive charges. So each of those OH bonds are polar. So the overall molecule is actually polar as well. So these water molecules also make really great a really great solvent because they can form what are called hydrogen bonds in many important solutions and also in our biology. So hydrogen bonds occur between a hydrogen on one molecule and then a very electronegative atom on another molecule. So if we had two water molecules kind of facing each other, they would want to orient themselves so that the partially negative oxygen is attracted or pointing towards the partially positive hydrogen. And then we create this hydrogen bond. But you'll learn more about that in general chemistry. These are just a few of the reasons why water is a really good solvent. Okay, so how do solutions actually form? Solutions form when the solute-solvent interactions are large enough to overcome the solute-solute interactions and the solvent-solvent interactions. So, for instance, we talked about previously how silver chloride, AgCl, is insoluble. And so that means it does not dissolve in water. And the reason for that is these solute interactions are just so strong, and water is not able to break them apart. Now, there's other examples of solute-solute interactions that are that you really can't break apart with water, and we'll get into that in a second. But additionally, you also would have to overcome the interactions between the water molecules. So if something can't break apart the water molecules, their hydrogen bonds, then you're just not going to form a solution. So the solute and the solvent have to interact with each other in order to form a solution. So in the figure off to the right, you can see that there are different, layers in these test tubes. And what these layers tell us is that the two, so the solute and the solvent that we would normally see in a solution, they're not mixing. They're what we say immiscible. So they do not mix. So one really good example is oil and water. Oil and water do not mix. They're immiscible. And that's because the oil-to-oil interactions are not strong enough to break apart water-water interactions, and vice versa. So they're just going to stay separate from each other. Now, solutions will form when the solute and solvent have similar polarities. So the common phrase you'll hear for this is like dissolves like. So polar solvents dissolve polar solutes, and then non-polar solvents dissolve non-polar solutes. So like dissolves like. So in our oil and water example, oil is non-polar and water is polar. So they are not going to mix with each other. All right, and in your textbook, there's a table 9.3 that goes through when solutions will form and when solutions will not form. So you'll notice in the solutions will form section, the solute and the solvent have to be the same. So polar and polar, those will dissolve in each other, so a solution will form. And then nonpolar and nonpolar will dissolve in each other, and so a solution will form. But if you have a polar and nonpolar solute and solvent, that's not going to form a solution, and vice versa. So you have to have the same type of solute and the same type of solvent in order for a mixture to occur. Okay, so let's look at an example. We're going to talk about methanol. So remember, this is that type of alcohol that you do not want to drink. It can cause organ failure. You can also go blind if you drink enough of it. So methanol is soluble in water because methanol has a polar OH group, and that can form those hydrogen bonds with water. So down below we have methanol molecules, and so if we draw the Lewis structure, and I'll just do this for you since we haven't really gone over this before. But methanol kind of looks like this structure I just drew. And if we looked up the electronegativity values for each of these atoms, we would find that carbon and hydrogen bonds are fairly nonpolar. But oxygen and hydrogen bonds are polar. So we do have polarity in that OH bond. So we have a partial negative on oxygen and a partial positive on hydrogen. So what that means is this is a polar molecule. And then we already talked about how water is polar as well. So if we add these two together, methanol and water, they're going to mix really well. So in our mixture off to the very right-hand side here, we have methanol molecules and water molecules, and they can form hydrogen bonds with each other because we have a partial negative oxygen and a partial positive hydrogen on the two separate molecules. So those are going to be attracted to each other. All right. Now, if we have a compound that contains a nonpolar molecule, such as iodine, oil, or grease, those do not dissolve in water because there are essentially no attractions between the particles of a nonpolar solute and the polar solvent. So let's talk about I2, iodine. The Lewis structure looks like this. And if we looked up the electronegativity values for iodine, we would see that, we have two iodine atoms. They're exactly the same electronegativity. So this is a nonpolar molecule because we have a nonpolar bond between those iodine atoms. So neither atom is really holding on to electrons more than the other atom. They're shared equally. So that means that water won't be able to dissolve this molecule because there's really nothing to interact with. Water would like to interact with partial positive, partial negative charges, or an ionic compound, which has full positive and full negative charges. But here, we just have a nonpolar molecule, and there's really nothing for water to attract to. So nonpolar solutes require nonpolar solvents for a solution to form. Now, one nonpolar solvent that's used fairly often is something called hexane. So this has 6 carbons all lined up in a row, essentially. And then there are hydrogens bonded to each carbon. I don't know if you could hear that car going by. We've been keeping our windows open since it's so hot, but it's very noisy. Okay, so this is what hexane looks like. And remember, the electronegativity values of carbon and hydrogen are pretty close together. So all of these different bonds are nonpolar. So this carbon-hydrogen bond is nonpolar. And of course, all of the hydrogen-carbon bonds are nonpolar. And then each of the carbon-carbon bonds are nonpolar because they're the same atoms. So that means the whole molecule is nonpolar. Now, nonpolar solvents can interact with nonpolar solutes. They have kind of similar properties, so they can actually mix together. So this would be a typical solvent. All right, and then ionic compounds, again, are able to dissolve in water as long as they are soluble. So this is where we would then consult our solubility rules. So sodium chloride is one of our soluble ionic compounds. So again, remember a long time ago we talked about how sodium chloride is a crystal. So it has alternating um, sodium ions in purple and chloride ions in green. And what ends up happening is water can interact with those charges. So for instance, the water molecule on the upper right there has a partial positive and partial negative charge. So the partial positive hydrogen is going to be attracted to the negative chloride ion. And multiple water molecules can kind of start to arrange themselves around that ion, and eventually they'll pull that ion away from the crystal. And then the same thing happens with sodium ions, except the partial negative charge on oxygen is attracted to the positive charge. So eventually we get these interactions as well that will pull sodium ions away until eventually the ionic compound dissolves. So off to the left we have an equation showing how that works. So sodium chloride initially starts out as a solid, and then it interacts with water to form separate ions. So we have sodium ions and chloride ions. Okay, so let's kind of go over what we just learned. So we'll do a couple of learning checks. So first, let's identify the solute in each of the following solutions. So remember, the solute is present in a lesser amount. Okay, so A, if we have 2 grams of sugar and 100 milliliters of water, which one would be the solute? The 2 grams of sugar. Another way to tell is that water is typically our solvent. So you could kind of automatically say, okay, the water should be the solvent and the sugar will be the solute. Okay, now what if we're mixing 2 liquids together? So in B, we have 60 milliliters of ethyl alcohol and 30 milliliters of methyl alcohol. So which one would be the solute? The 30 milliliters of methyl alcohol, because that is the smaller amount. All right, so now in C, we have 55 milliliters of water and 1.5 grams of sodium chloride. So which one would be the solute? Sodium chloride, because that is present in not only a smaller amount, but also remember water is typically our solvent. Okay, now air is our last example. So if air consists of 200 milliliters of oxygen and 800 milliliters of nitrogen, which one is the solute? The 200 milliliters of oxygen. Great. All right, and here are the solution slides. So now let's do another learning check. Let's say we add solid lithium chloride to water and it dissolves. Why does it dissolve? So what are the lithium ions attracted to? Are they attracted to the oxygen atom of water, which is partially negatively charged? Or are they attracted to the hydrogen atom, or the partially positive part of water? So lithium ions are positively charged, and remember, opposites attract in terms of charge. So that would be attracted to the oxygen atom. And what would the chloride ions be attracted to? Are they attracted to the partially negative oxygen or the partially positive hydrogen? The partially positive hydrogen. So chloride ions are negatively charged, so they would be attracted to the partially positive charge on water. All right. And then let's do one more learning check. Which of the following solutes will dissolve in water and why? Okay, so let's look at A. We have sodium sulfate. Okay, so what type of molecule is this? Is this an ionic compound? Is it a polar molecule? Or is it a non-polar molecule? So sodium has a positive charge and sulfate has a negative charge. So this would be an ionic compound. Okay. Now, water usually does dissolve ionic compounds unless they're insoluble. So let's make sure that this is a soluble ionic compound. So let's go back and think about our solubility rules. Okay, so we have sodium ions and sulfate ions. Now, in our solubility rules, sodium ions are always soluble no matter what they're bonded to. And then sulfate ions are generally soluble with a couple of exceptions. So this would be a soluble compound because of sodium in particular. Okay, so that means that sodium sulfate will dissolve in water. Okay, so that one really combined a lot of different concepts from this quarter. Now, what about part B? We have gasoline, which we're told is non-polar. Will that dissolve in water? No. So this will not dissolve, or let's just write, does not dissolve. And that's simply because it's nonpolar. Remember, like dissolves like, and water is polar. So water will only dissolve other polar molecules. Okay, so let's move on to C. We have iodine, I2. Now, is that an ionic compound? Is it a polar compound, or is it a non-polar compound? So earlier we said that this is a non-polar compound, and that's just because we have two of the same atom, so they're sharing electrons equally. So there aren't any partial positive or partial negative charges. So would this molecule dissolve in water? No, because it's nonpolar and like dissolves like. All right, what about D, HCl? We have hydrochloric acid. Is this an ionic compound, a polar compound, or a nonpolar compound? This one we need the electronegativity chart for. So on a quiz, I would give you the electronegativity chart. And hydrogen has a value of 2.1. Chlorine has a value of 3.0. So if we take the difference between those, we get a difference in electronegativity equal to 0.9. And remember, if the difference in electronegativity is 0.5 or greater, then it is polar. So hydrochloric acid is a polar molecule. So will that dissolve in water? Yes. So remember, like dissolves like. So a polar molecule will dissolve a polar molecule. All right, so hopefully that helps a little bit with figuring out what dissolves in what. So when do solutions form and how they form. So next time we're going to talk about electrolytes and non-electrolytes. So we kind of talked about this before when we were discussing ionic compounds and how they dissolve, but we'll go into a little more detail. So I will see you then.